Notes 1, 2, we're going to be looking at graphs of inverses. So on this front page, what we're going to do is we're going to create a table of values in table 1 for the given equation, and then we're going to plot those points. Then we're going to switch the x and y coordinates, and then record those in table 2. Okay? Then we're going to plot those points, and we're going to draw the line y equals x as a dotted line, and then we're going to look for some patterns. Okay, so this first equation here, we have y equals 2 to the x. This is an exponential equation. Remember that it curves, and the ones that we've looked at were approaching the x-axis. Okay, so we're going to, if you don't have a calculator, you can easily just plug in some values for x in that exponent and then work it out. If you do have a calculator, you can plug it into y equals, so 2 to the x power. You can graph it first if you want to see what it looks like, and then go to your table. Let's go from -2 to 3. So -2 would be 0.25, -1 would be 0.5, 0, 1, 1, 2, 2, 4, and 3, 8. So let's go ahead and plot those points. Okay, so make sure that when you connect your points that it's not touching the x-axis nor going below it. Alright, so we did that part of it. Now we're going to flip the x and y, or switch the x and y coordinates and put them in table 2. So 0.25, -2, 0.5, -1, 1, 0, 2, 1, 4, 2, and 8, 3. So notice on this one that it's approaching the y-axis. And I'm going to go ahead and label these so that way I know which one's which. This is table 2, and this is table 1. Alright, so then notice that it said you're going to draw the line y equals x. When we have the line y equals x, the slope would be 1 over 1, and the y-intercept, notice there's not a number there, so it would be 0. So that line would be crossing the y at 0, and then up 1, right 1. So 1, 1, 2, 2, 3, 3, and so on. So I'm going to go ahead and just make that my dotted line there. Okay, so we're going to move on to number 2, and then we're going to look for a pattern. So notice number 2, we have a linear equation, so it should be a straight line when we graph it. So you can either use slope and y-intercept, graph it that way, or use the calculator. So let's just go from -3 to 3. So -3, 10, -2, 7, -1, 4, 0, 1, 1, -2, 2, -5, and 3, -8. So we're going to go ahead and plot those points. So -3, 10, -2, 7, and then we can continue that. Alright, so to find the other line, we're just going to switch our x and y, so 10, -3, 7, -2, 4, -1, 1, 0, -2, 1, -2, 5, 2, and negative 8, 3. So plot those points.
Any results yet? Who won?
Sorry. Okay, and then we're going to graph that y equals x line as a dotted line. Now, I want you to look at number 1 and number 2. Look at the two graphs that you have. Look at also that line y equals x. You're looking for a pattern on both examples. Okay, so you should notice that there's a reflection across that dotted line that we drew in the middle. Those points were reflected across that line y equals x. So that's what we're going to put where it says what do you observe? So when you switch the x and y coordinates, then the graph is reflected across the line y equals x. So anytime you're switching the x and y coordinates and then graphing a new graph, then that is just making a reflection across the line y equals x. Okay, so the back, it says when two graphs are reflections of each other, which we just talked about over the line y equals x, then they are said to be inverses of each other. So anytime there's a reflection across the line y equals x, which means you're switching the x and y coordinates, those are inverses. So since number 3, it says find the inverse of the relation. The relation just means the original. So anytime it says relation, it's talking about the original. So if we're given points to find the inverse points, all we're going to do is switch the x and y coordinates. So the first one would be negative 3, 4, negative 1, 2, 0, 7, 4, negative 1, and 10, 2. Alright, the next part, we're going to graph each of the following functions. Then we're going to graph the line y equals x as a dotted line. We're going to reflect those points to find the inverse graph. Once you've done that, you're going to determine if the inverse is a function. So remember back when we were talking about functions, to determine if a graph is a function, we're going to use the vertical line test or the pencil test. Remember, a function doesn't have any repeating x values, so that's why you use the vertical line test to determine if it's a function or not. So notice on 4, we have a linear equation. If we are going to use the calculator, then we need to, or graph it, doesn't really matter, we need to get y by itself. So we're going to subtract 2x. Notice we have a negative y, so to make it a positive, we would divide everything by negative 1. So now we have positive y equals 2x minus 5. So you can either plug it into the calculator and find those points in the table, or use slope and y-intercept. It doesn't really matter. So if we plug it in, so we'll go from negative 2 to 3. We should have a straight line when we graph it because it's linear. So negative 2, negative 9. 0, -5, and then 1, -3, 2, -1, and 3, 1. You can continue that because you know your slope is going up to right 1. So there's our relation, the original. Now we're going to graph our line y equals x as a dotted line. And then we're going to graph the inverse. You can reflect it over that line just by looking to see how far it is on one side and then same distance on the other side, or just switch those x and y coordinates. So instead of it being -2, -9, it's going to be -9, -2, -1, or -7, -1 is -5, 0. -3, 1, -1, 2, and you can continue that by using the slope there. I want you to label that as the inverse graph, which is your second one, because we have to determine if the inverse is a function. So we're only looking at the second one. So we're using the vertical line test. So if I were to draw vertical lines, notice looking at only the blue, it would only intersect it at one point, which means this would be a function. Okay, so using the vertical line test, but we're only looking at that inverse graph. Okay, 5, notice this is quadratic. This is the quadratic parent function. We've already gone over this. So you can plug it in the calculator if needed, but I already know what those points are. If we plug in a -3 and we square it, we're going to get a +9. -2 squared would be 4. -1 squared would be 1. 0 squared would be 0. 1 squared would be 1. 2 squared would be 4. And 3 squared would be 9. So we're going to plot those points. It should be a parabola because this is a quadratic. -3, 9. -2, 4. -1, 1. 0, 0. 1, 1. 2, 4, and 3, 9. So there's my original there. We're going to draw or sketch your y equals x line as a dotted line. And then we're going to reflect to find our inverse graph. So you can either look at it and reflect it, or just switch the x and y coordinates. So my first point will be 9, -3. 4, -2. 1, -1. 0, 0. 1, 1. 4, 2. And 9, 3. And that is my inverse. That was the second one that we graphed. So notice when we have a parabola, we reflect it across the line y equals x. It should be a sideways parabola. Okay, so now we're going to determine if the inverse is a function. So we're only looking at the blue one. So we would use the vertical line test. If I do that, notice when I draw vertical lines, it's intersecting at two different places, which means the inverse would not be a function. And I wrote yes. It should be no. So the inverse is not a function there. The relation is the original, but not the inverse. Okay, so there is a way that you can figure out if the inverse is a function without even graphing the inverse. So the inverse of a function f is also a function if and only if no horizontal line intersects the graph more than once. So it's called the horizontal line test. It's also said to be one-to-one if no horizontal line intersects its graph more than once. Okay, so what we're going to do on these next couple of examples, we're going to graph each and use the horizontal line test to determine if the inverse is a function in one-to-one. But we are not going to actually graph the inverse like we did on those other examples. Okay, so look at number 6. It's quadratic. So let's plug it in. Negative x squared means it's going to be opening down. Notice it opens down. We're going to go to the table. So we have negative 3, negative 5, negative 2, 0, negative 1, 3, 0, 4, 1, 3, 2, 0, and 3, 5, negative 5. Okay? Alright, so let's plot those points. Negative 3, negative 5, negative 2, 0, negative 1, 3, 0, 4, 1, 3, 2, 0, and 3, 5. Okay, so we're not going to graph the inverse. We're just going to use the horizontal line test to determine if the inverse is a function in one-to-one. So if I were to draw horizontal lines through the relation, which is the original, notice it intersects at 2 different places, which means the inverse would not be a function. So we can use the horizontal line test to determine if our inverse is a function or not. Okay? Alright, let's look at this last one. Y equals x cubed. We have not looked at this before. This is called a cubic graph. Okay? So you can plug it in the calculator, but I'm just going to plug some values in, but you can use a calculator if you want to. So I'm going to plug in a negative 2, but when I cube it, that's going to give me a negative 8. Plugging in a negative 1 and I cube it, I get negative 1. 0, I get 0. 1, I get 1. And 2 cubed gives me 8. So let's plot those points. Negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1. And 2, 8. So notice here when you connect them, it looks like a snake. So this is a cubic graph here. We're determining if the inverse of this would be a function or not. So we're going to use the horizontal line test. So when you draw horizontal lines, notice that it's only intersecting at one place, which means the inverse would be a function. Okay? So to find the inverse graph, all you're doing is reflecting it across the line y equals x, or just switching the x and y coordinates, which is the same thing.